Good morning and welcome you all to this course on fluid machines. Now, in this class, before discussion on axial flow machines, a very brief introduction of the axial flow pump, I will first discuss the characteristics of pumps in series and parallel, which were left earlier. We have discussed the head discharge characteristics of a pump, how this can be how the head discharge characteristics at one speed and diameter, from one speed and diameter we can generate head discharge characteristics at different speed, pump speed and diameter. And at the same time we have recognized the operating point as the intersection of the system characteristics and the head discharge characteristics of the pump. So, all these things we have discussed. Now, first we will discuss the operations of pumps in series and parallel. Sometimes the multiple pumps, more than one pumps are required depending upon the requirement, the use, where a very high head is required to be generated, which cannot be met by a single pump. We use more than one pumps, two or more pumps in series. Series means the discharge of one pump is attached to the inlet of the other pump and so on, by which what happens, the head developed of each pump is being added together to find out the total head developed of the system of pumps in series. So, let us first see the pumps in series. If we have two pumps in series, okay, that means the inlet of one pump, that means let us now show by a box only, that pump 1, everything we know, that impeller, diffuser. So, unnecessarily I am not drawing that. This is the inlet of pump 1 and the outlet of pump 1 goes to the this way to the inlet of pump 2, the inlet of pump 2 and ultimately the outlet of pump 2. Let us consider 2 pump is the final discharge. So, therefore, you see the head developed by pump 1 is the difference of head at inlet and outlet. This is the head developed. Let this head inlet is HI and let this is the outlet head. This is the outlet head of pump 1 and let this is the inlet head of pump 1, this is the inlet head of pump 2 and this is the outlet head of pump 2, which is equal to the head delivered. Now, it is common sense that you see that the head developed by pump 1 is HO1 minus HI1 and this HO1 is equal to HI2 because they are connected in series. So, the loss through this pipeline connecting this is very small, this is a very short pipe, they are just connected, coupled. So, HI2 and this HO2 minus HI2 is the head developed by the pump 2. Therefore, the total head developed is HO minus HI1 is the head developed by pump 1, head developed by pump 1 by pump 1, this is the head developed H plus head developed by pump 2, whereas the same flow is going Q, Q remains same. This is the series connection, it's most simple thing. So, if we now draw the characteristic curve, we will see that now these two pumps may be identical one, may be different pumps also. Let us consider the identical pump, it will be easier to draw the diagram. So, let the single, for the single pump, this is the head discharge characteristics for the single pump. So, the head discharge characteristics of the combined pump is very simple. For each and every discharge, we just add the head and we get the head discharge characteristics of the head discharge characteristics of the, this is the curve. This is the curve. This ends here at the same point where it is 0. That means, at any point Q, if this be the head developed H1 by this is H1 by this pump, one pump, then this will be also H1. That means twice H1. Now, this will be H1. That means twice of this H. Similarly, here also at any other point, if this is H2, then this will also be H2, because heads are added. So, therefore, for any Q, the head of the combined pump in series is double that of the single pump, since the pumps are identical. But the interesting thing is that if we draw the system characteristics, this is HS, the system characteristics, this is system characteristics, this is system characteristic, the system characteristic. Then you see, this was the operating point for the single pump, and this will be the operating point for the combined pump, where this is not doubled. For example, here if this be the head of the single pump, the operating pump head is here, which is doubled. That means, though the discharge characteristics for the identical pump in series show the head to be doubled at a given discharge, but the operating point, this is the head discharge characteristics, operating point, the head is increased. That means, in actual operation there is an increase in the head, but it is not doubled in case of identical pump. So, therefore, increase in head is seen, that this head is higher than this. So, this depends upon the system characteristic curve. Okay. So, therefore, the operating point shows like that, but the head discharge curve is, the head discharge curve is generated like that. If the pumps are different, so we have to add the, we have to draw the two head discharge curve, and the heads have to be added and to be drawn like that. This is the head discharge curve for pumps in series. Similarly, for pumps in parallel, where the requirement of discharge is more, which cannot be made by a single pump, individual pump, there the pumps are connected in parallel. That means, pump 1 and pump 2 are connected in parallel. Pump 2, that is pump 1, pump 2 are connected in parallel. So, they take, for example, the same source, same sump or something like that, but they are discharging the same line, and from where the final discharge is there. That means, here what happens, the Q1 and Q2 of the two pump is being added to, just like the parallel connection what happens series, but the head developed by pump 1 and pump 2 will be same, because they are connecting to the same main line. So, that the head here is the same for both the pumps. So, this is the head, final head available. So, H of pump 1, head developed by pump 1 equal to head developed by pump 2, head developed by pump 2, but the flow rate is added, the discharge is added for pump 1 and pump 2 give the final discharge. That is the pump in series. Here also we can draw the discharge characteristics. If we consider the two identical pump, pump 1 and pump 2 identical, and we have a head discharge curve like this for the one pump, here what happens, the discharge is added, the flow rates are added. So, therefore, for any head, given head, the flow rates will be added. It starts from here and ultimately show like this. That means, this is not correct in the scale, because this discharge and this has to be same. However, this is little awkward, but you just take it that this is Q at any head and this is also Q. This should be same. However, my drawing in that scale, the space is limited, so this is not correct. So, this Q has to be same. Here you can better represent, let Q1 Q1, here Q2, and this is the same Q2. Okay, that means Q's are added at a particular age. So, this way we can generate, and in the same way we can tell that if we have the resistance, system resistance like this is the HS for example, the static lift, then the operating point is here and operating point is here. So, here the operating point, the discharge is increased from that of the operating point with the individual pump, but not it is doubled, but here it is doubled. The discharge what was here is doubled here. So, it cuts here, this slopes like this is a parabola. Okay. So, therefore, operating point here also gives a higher discharge, which is the objective of pumps in parallel, but this is not the double in case of two identical pumps. That means, this is not the addition of the two flow rates. That means, this is the addition of the two flow rate is the final flow rate we tell, not in case of operation. That is when we find out the characteristic things, curve. But in actual operation, when it is added or when it is integrated with the system, then the two flow rates addition will not be the final flow rate, it will be different. In the similar way as we saw that this thing for a series pump in series also, it is different, though we told that the head developed is head developed by the pump 1, pump 2, that is when we think of the discharge characteristics, but actual head developed in case of operations with a system, that is pipes, valves, everything, the transmission pipe. So, that system characteristics is added with the pump, then the operation point will give a head higher than this head developed by pump 1 or head developed by pump 2 in case of identical pump, or it will be less than the sum of these two, double of that or sum of these two. Okay. It will be higher than the individual head developed, but less than that of the sum of these two. Similar is the case. This is because of the fact that operating point is the point of intersection of the system characteristics and the HQ or head discharge characteristics of the pump. So, this way we have an idea that how we can get the head discharge characteristics of pumps in series and pumps in parallel, and the requirement for that where the pumps in series is required or the pumps in parallel is required. Now, we will discuss an axial flow pump. Now, first of all I tell you the axial flow pump is just the converse of an axial flow turbine. If you recollect that axial flow turbine concept came to give a higher efficiency and to give a high power developed by the turbine when the head is very low. A substantial amount of flow has to take place to the runner, for which a demand in the axial flow turbine comes. Similarly, axial flow pumps also comes into picture when we have to deliver a higher flow rate, okay, and a relatively lower head. So, the concept of axial flow pump comes into picture. Now, the axial flow pump looks like this. Basically, I just explain you that this basically looks like the converse of a axial flow reaction turbine. It consists of a central boss, which this is the central boss or hub on which the rotor discs are mounted, and this is a cylindrical casing, and there is clearance between this rotor and the casing. This clearance should be made as less as possible to avoid leakage, and this is rotated, this rotates, and these blades are mounted in a way that the fluid comes axially, the water flows axially through these blades, and there are inlet guide vanes. You see, these are fixed this is fixed to the stationary inlet guide vanes to the casing. This we see a frontal view. So, there are stationary, see the guide vanes, and the purpose of this guide vane is to direct the water or the liquid properly to the rotating blades of the axial pump in the proper angle to the rotating blades without shock, that means matching the inlet angle of the blades. This is the function of the inlet guide vanes. Now, there are also at the outlet some stationary vanes are there which are also guide vanes fixed to that. The purpose of this is to reduce the swirl. That means, when the liquid comes, that water comes out of these blades, this has got a substantial swirling component of velocity along with the axial component of velocity, and this swirling component of velocity is being reduced while flowing through this stationary blade, and finally it goes out of this blade and out of the machine. This is overall a picture of this axial flow pump, and here two information you can take, that the number of impeller blades or the rotor blades, number of impeller blades or rotor blades usually varies from 2 to 8, and the ratio of half diameter to the rotor diameter is equal to 0.3 to 0.6. It is almost similar to that of the axial flow turbine, that is the Kaplan turbine. It looks like that, the blades are like that, but here the axial flow is similar to the turbine. So, at entry at all inlet the radial locations vary, all outlet at radial location vary. So, the radial location at inlet and outlet do not change, that means there is no change in the u component of velocities at inlet and outlet. So, at all radial locations inlet is there, at all radial location you see here, at all radial locations the inlet is there, all radial locations the outlet. So, here the blade velocity u is usually defined in this type of axial flow machines at a mean radius. So, therefore, if we write the head developed part of the pump, head developed, that is equal to V2 square minus V1 square by 2g plus U2 square minus U1 square by 2g plus VR1 square minus VR2 square by 2g, just the minus sign for that of the turbine. Now, here U2, U1 is same. So, one is the increase in its kinetic energy or the velocity, and another is the increase in static head because of the increase in radial velocity, rather decrease in radial velocity from that at the inlet. So, that these blade passages are diverging type. In case of an axial flow turbine, it was converging type, diverging type. So, that the VR1, that is the VR2, that is the relative velocity with respect to the blade at the outlet is less than that at the inlet. So, that this becomes positive, and this is manifested in terms of the rise in pressure. So, this is the function of any axial flow machine. In case of pump, this is like this, in case of turbine, that the sign changes. So, therefore, it is only the change in the relative velocity that the flow passage is accordingly designed. It is converging in case of turbine, and it is diverging in case of pump. Flow is mainly in the axial direction. It has both axial and tangential component of velocity, but the swirling or tangential component of velocity coming out of the blade is being reduced while flowing through the static guide vanes at the outlet. So, these all are the main parts, and this is in brief the axial flow pump. So, with this I will end the lecture on rotodynamic machines, the machines which functions on the change of angular momentum of the fluid in course of a continuous flow of fluid through the machines having a relative motions between the rotor of the machine and the fluid. And we have discussed turbines, impulse reactions, and also the centrifugal pump and the axial flow pump. Next, I will discuss the positive displacement type of pump machines, mainly the positive displacement pump, reciprocating pump in the next class. So, for today, thank you.